I wanted to do some more in section 9.2. We're looking at graphing polar equations, and I had 12 equations that I wanted us to go through. We've already done the first 7, and so we'll pick up with problem 8 here. I went over the polar symmetry tests in the last video, and I'll be using that for the next few examples here. So let's take a look at problem 8. We want to graph the equation r equals 1 plus sine theta. So I'm going to begin by using a table of numbers here, and I'll gather up some points, and then I'll consider using any symmetry later on. So if I were to let theta be 0, sine of 0 is 0, which means that r would be 1. Okay, so here's 1, 0 on the graph. Remember, we're plotting the points in the order r theta. Okay, if theta is pi over 6, sine pi over 6 is 1/2. Plus 1 would be 3/2 then for r. So on the pi over 6 radial line, I want to go out 3/2 units. Of course, on the polar grid here, it's probably easier to draw that. Here's the pi over 6 axis. I'm going out 3/2 units and plotting that point there. Okay, and I'll let theta be pi over 4 next. Sine pi over 4 is 1 over root 2. If you 1 over root 2 is roughly about 0.71, and then if you add 1 to that, roughly 1.7 then would be the r value there. So on the pi over 4 radial line, I want to go out about 1.7 units there. Okay, if I let theta be pi over 2 next, sine pi over 2 is 1, plus 1 is 2 for r, so here's 2 pi over 2. And then I'm going to jump to 3 pi over 2 next. If theta is 3 pi over 2, sine 3 pi over 2 is negative 1. Plus 1 is 0 for r. So on the 3 pi over 2 radial line, I want to go out 0 units. That'll put me right at the pole. If I let theta be 11 pi over 6, sine of pi over 6 is 1/2. If you flip that triangle into quadrant 4, that's going to affect the opposite side, and that would be a negative 1. So sine of 11 pi over 6 would be negative 1/2. Add 1 to that, and r would be 1/2. So here's the 11 pi over 6 radial line. You want to go at a 1/2 unit on that and plot that next point. All right. The part of the curve that I've got drawn in pencil is what we have so far from this table. And the next thing that I want to consider is if there's any symmetry. In particular, I'm wondering, is the graph symmetric to the vertical line theta equal pi over 2? Well, to check that, I would want to replace theta by pi minus theta and check and see if I get the same equation as I had started off with. All right, so I've done that below. Replace theta by pi minus theta. Sine of pi minus theta, I'm using an identity. That's our sum and difference formula that was on that sheet that I gave you there in chapter 7. Of course, that's not a formula that you have to have memorized or anything, but I'm using the sum and difference formula there. And so sine of pi minus theta is the same as sine pi times cosine theta minus cosine pi times sine theta. Sine pi is 0, so that's going to knock out this middle term here. Cosine pi is negative 1. 1 minus negative sine theta would be the same as 1 plus sine theta for r, and that's the same equation as we were originally given there, r equal 1 plus sine theta. So this calculation tells me that this graph is going to be symmetric to the vertical line theta equal pi over 2. So all these points can be reflected to the other side here, completing the graph. This curve is called a cardioid. This is one of the famous curves that you would see in polar coordinates in the polar coordinate system. You will do lots of things actually with cardioids in Calc 2. And I'll comment on a cardioid again here after we've done the next 2 problems. So Here's another one, problem 9 on that sheet. We want to graph r equal 3 plus 2 cosine theta. Now it might seem, by the way, like I've got maybe some minimal changes here. Just the slightest little change in polar coordinate form can drastically affect the graph. Okay, so let's take a look at this next one. And again, I'm going to start with a table and then consider using any symmetry after I've got some points plotted. If theta is 0, cosine 0 is 1, times 2 is 2, plus 3 is 5. So on the 0 radial line, I'll go out 5 units there and plot a point. If theta is pi over 6, cosine pi over 6 would be root 3 over 2. Times 2, the 2's cancel, and that leaves me with root 3. Root 3 is about 1.73 if you go nearest 2 digits. And then if you add 3 to that, roughly 4.73 would be the r value. Okay, so here's the pi over 6 radial line. I want to go out roughly about 4.73 units and plot that next point. If I let theta be pi over 3 next, cosine pi over 3 is 1/2. Times 2 is 1. Plus 3 is 4 for r. Okay, so here's the pi over 3 radial line. You want to go up 4 units on that one and plot a point. If we let theta be pi over 2 next, cosine pi over 2 is 0, which means that r would be 3. Okay, so here's 3 pi over 2. If theta is 2 pi over 3, cosine of pi over 3 is 1/2. Okay, if you flip that triangle into quadrant 2, then the adjacent side would be a negative. So cosine of 2 pi over 3 is negative 1/2. Times 2 is negative 1, plus 3 is 2. So I want to go 2 units on the 2 pi over 3 axis. Plot that next point. Here's if theta is 5 pi over 6, cosine of pi over 6 is root 3 over 2. If you flip that triangle into quadrant 2, then that's going to affect the adjacent side, and that would be a negative. So cosine of 5 pi over 6 is negative root 3 over 2. Times 2, the 2's cancel, and that leaves me with 3 minus root 3. Root 3 is roughly about 1.73, so if you have 3 minus 1.73, you'd end up getting 1.27. You know, and again, that's an approximation, but so that'd be my next point here. On the 5 pi over 6 radial line, you'd go out roughly about 1.27 units. And then I'm taking theta to be pi. Okay, cosine pi is negative 1, times 2 is negative 2, plus 3 is 1. So on the pi axis, I want to go out 1 unit there. And the part of the graph that you see is drawn in pencil would be what we have so far from the table. Now the next thing I'm wondering is maybe if the graph is symmetric to the polar axis. The polar axis is the same as the x-axis. And to check that, I need to replace theta by negative theta and see if I get the same equation. So I've done that. Replace theta with a negative theta. Cosine negative theta, same as cosine theta, right? Because cosine is an even function. So I'm looking at r equals 3 plus 2 cosine theta. That was what we had originally there. And so this calculation would tell me then that the graph is symmetric to the polar axis. So all these points can be reflected about the x-axis there to finish the graph. Okay, this curve is called a lemmason. That C with the squiggle below it is an S sound. The word lemmason is a French word. Okay, and a cardioid is what we had looked at over here is a curve that would be in the lemmason family. Okay, of curves, and I'll talk about that here after we've looked at the next graph. Okay, and all right, so let's take a look at this. And by the way, in a lemmason, we don't have a sharp turn. Okay, a cardioid is going to produce a sharp turn there at the pole, and in this picture, we have a nice smooth turn, not at the pole. Okay, and that's a feature of a lemmason. All right, and by the way, a couple things here. So probably something that you've noticed here in these last couple of examples is that there's symmetry going on. Okay, Symmetry is a common thing when you're working with polar coordinates. Like lots of graphs in the polar coordinate system are going to be symmetric. Okay, so that's one thing that you'd probably want to consider, in a lot of problems to save time with, making a table and plotting points. Okay. Another thing too is if I had like the equation r equal 3 plus 2 sine theta, that would also be a limicon. The only change from what we would have here would be a rotation 90 degrees. Okay, and we'd be looking at a lemison top to bottom rather than left to right. In this case, if I had like r equal 1 plus cosine theta, that would still be a cardioid. It's just the cardioid wouldn't be top to bottom; it'd be left to right type deal. It'd be a rotation through the pole. So something to keep in mind. Okay. Here's another one. Problem 10. We want to graph the equation r equal 1 plus 2 cosine theta. So I'm starting with a table here, and I'll consider using any symmetry later. If theta is 0, cosine of 0 is 1, times 2 is 2, plus 1 is 3. So 3, 0 would be the first point there on the graph. If theta is pi over 6, cosine pi over 6 is a root 3 over 2, times 2, the 2's cancel, and that would leave me with 1 plus root 3. Root 3 is roughly about 1.73 if you go nearest 2 digits. Add 1 to that, and I'm getting 2.73 then, roughly, to the nearest 2 digits. So there's that next point. Okay, if I let theta be pi over 3, cosine pi over 3 is 1/2, times 2 is 1, plus 1 is 2. Go 2 units out on the pi over 3 axis. If I let theta be pi over 2, cosine pi over 2 is 0, so r would be 1. Here's 1 pi over 2. And if I let theta be 2 pi over 3, cosine pi over 3 is 1/2. If you flip that triangle into quadrant 2, that's going to affect the adjacent side, and that'd be a negative 1. So cosine of 2 pi over 3, that'd be negative 1/2. Times 2 is negative 1, plus 1 is 0. Okay, on the 2 pi over 3 radial line, go out 0 units, or that's going to put you right at the pole. Here's 5 pi over 6. If we plug that number in next, cosine of pi over 6 is root 3 over 2. If you flip that triangle over into quadrant 2, then the adjacent side would be a negative root 3. So cosine of 5 pi over 6, that'd be negative root 3 over 2. Times 2, the 2's cancel, and that would leave you with 1 minus root 3. Root 3 is roughly about 1.73, so 1 minus 1.73 would be negative 0.73. On the 5 pi over 6 radial line, you're going to go in the opposite direction, 0.73 units. And that's going to put you into quadrant 4 here in this spot. And I'm taking pi next, so plug that in. Cosine pi is negative 1, times 2 is negative 2, plus 1 is negative 1. Okay, on the pi axis, go in the opposite direction, 1 unit, and that'll put you at this spot here at negative 1 pi. Okay, so here's what I have going on so far, this curve that I've got drawn in pencil so far, and I want to see if maybe this graph is symmetric to the polar axis, the x-axis. So again, I'll need to replace theta with a negative theta, and so I've done that here, and check and see if I get the same equation. Cosine of negative theta, the same as cosine theta, and so in fact I would get the same equation, as I had originally started off with. So this calculation would tell me that this graph is going to be symmetric to the polar axis. So all these points can be reflected about the x-axis, completing the graph. And the curve that we have drawn is a lemison with a loop. Okay, and here would be the complete graph then on my polar grid. Again, if you want any of this polar graph paper, send me an email and I can, send you this graph paper. It's kind of handy to have, if you're working with polar coordinates. So we have a lemison with a loop. Okay, and just a summary on the next page here, the difference between cardioids and lemmasons is as follows. So if you have the equation r equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta, you're going to be working with a cardioid or a lemmason. Okay, you'll have a cardioid if a and b are the same number. So like over here in problem 8, we had a cardioid because a is 1 and b is 1. It would still be a cardioid if I had a minus sign there. Okay. You're going to have a lemmason if a is greater than b. So in this problem number 9 here, a was 3 and b was 2. And we end up getting just an ordinary lemmason. A cardioid is different from from an ordinary lemmason in that there's a sharp turn at the pole. Okay, that's a feature of a cardioid. A lemmason has a smooth turn going through the axis there. And then you're going to have a lemmason with a loop if b is greater than a. So in my last problem here, b is 2, a is 1, 2 is bigger than 1, so we end up getting a lemmason with a loop. The bigger that b is compared to a, the bigger the loop that will be created inside the lemmason there. Right? So basically, the point of this would be to say that the form of the equation can tell us what we're going to be drawing, and that's a handy thing to know. Just like it would be in algebra. If I'm talking about a parabola, everybody knows what a parabola is, okay? And the form that would be representing the equation, okay? Or there's other basic functions that we talk about in algebra. Same deal here with polar coordinates. There's some graphs that come up over and over and over again, and the form is probably worth knowing. A lemmason is, one of the common graphs that you'd work with in polar coordinate in the polar coordinate system. So we'll stop the video there.